Hi everyone, I'm Jared Makario, a former research assistant at Center for Data Science and Artificial Intelligence at Dedan Kimathi University of Technology. On behalf of my co-author, Dr. Shira Wamaina, I am going to share about work we have done on a Bluetooth low energy based system for livestock tracking and localization. To begin, livestock production is one of the main supplementary sources of livelihood in Kenya after crop farming. It has gained momentum due to climate change and its impact on agriculture, increase in population and demand for livestock products. It accounts for 12% of Kenya's gross domestic product and is practiced in various geographical regions with varied climatic conditions. In this case, small-scale farmers contribute 90% of beef production and 80% of milk production, according to 2019 political report. Farmers face many challenges including livestock theft where animals are stolen, animals getting lost in the field in the case of free-range animals. Also, they have limited access to veterinary and animal husbandry services as well as livestock management technologies. They keep various livestock animals such as cows, goats, sheep, among others, as shown in figure 1, whereby the livestock are pasturing. They also have challenges pertaining to performing veterinary activities such as medication and quarantine. In addition, if the numbers of animals increase, tracking the number is hard. They also need solutions to manage the resources such as water and pasture. So this proposed BLE system tracks, counts, locates specific animals using BLE protocol for data communication, whereby caller devices advertise animal data such as names, and central device collects the information and counts the number and displays on a local display. Available methods face range, connectivity, cost and power challenges, which has led to limited outdoor applications such as identification and management. Available methods include global positioning system, GPS, ear tags, and RFID. The objectives of this work include to design farm animal management BLE IoT-based solution to monitor animals, to develop peripheral core devices, to advertise data information pertaining to animals, to develop a central device for scanning animals' data and visualizing, and finally to deploy the solutions at the goods farm on sheep and goats. The design of this work is built around Arduino Nano 33 BLE Sense development board with specific features of interest such as the ARM Cortex M4 processor with NRF 52840, a Bluetooth 5 stack that we are using for communication, and low power consumption capabilities and libraries available for this development. Since this work is BLE based, we need to understand what BLE entails. It is simply a wireless personal area network technology designed and marketed by a Bluetooth Special Interest Group, Bluetooth CSIG, aimed at novel applications, for instance healthcare, fitness and beacons, among others. This is a definition according to Wikipedia. It belongs to the unlicensed industrial scientific medical band and operates at a frequency of 2.4 GHz. In recent advancements on range and improved power management, it has extended its applications to other areas such as industries and agriculture, among others. We designed the system bearing in mind tracking, counting, localizing, power management and range in mind. The oval objects represent caller devices, or sometimes known as peripheral devices, or sometimes regarded as server devices for both sheep and goats. The central device, sometimes regarded as client device, is represented by a box on the figure with a BLE receiver, a 4-digit 7-segment common cathode display, and a multiplexing circuit. A C++ advertising program is flashed on the caller device and powered up. They advertise the information pertaining to the animals wearing them within a given range. The central device scanning, tracking, counting, and localizing sketch is also loaded onto the central device and powered up. When the caller device within range is detected, the central device obtains the MAC address, the animal ID, among other parameters, and counting is done and visualized on the display. If specific animal is needed for certain reasons, the central device tracks and locates the animal using a buzzer built on board, which goes on when the animal is within specified range. We started with doing Bluetooth range testing by setting up an experiment of successful data transmissions from a caller device to the central device. So peripheral device was moved away from the central device at a 1 meter interval until no more data packets were being received. The RSSI was plotted against range in meters, and power sources varied from time to time. It was found out that the range increased as power supply was also increased, as shown in the figure 5. An average range of 12 meters of radius was recorded. The central device is designed with a 4-digit display, a buzzer, multiplexing circuit, and Arduino MCU. A prototype is designed on a breadboard, after which it is designed on KiCad open source design software. The circuit is printed out and transferred to the PCB board using heat. It is later aged in sodium persulfate solution. The traces are cleaned, component holes drilled, they are soldered, and the circuit powered up for testing as shown in the processes A to H. On caller device design and development, Arduino MCU and 350 mAh battery and a switch were used and assembled in the collar casing. It has the following features. Each collar weighs a total of 82 grams and the battery life is up to 10 days. This is whereby we have a 2-second advertising interval. It has a long and adjustable strap to adjust and comfortably fit around the neck of the animal, and we tried to, as much as possible, to make the casing waterproof. The system was deployed at the Coutts Farm dairy section on a sheep and a goat for a whole day. The central device scanned, tracked, counted, and located the animals with the collar devices, as shown in figure 10. The number is displayed on the 4-digit 7-segment display. And using RSSI and a buzzer, the collar devices were tracked and retrieved from the flock when the central device was within a 2-meter radius. This work has shown that livestock production can be enhanced by leveraging low-cost BLE-based system. Tracking and localizing the animals makes management of livestock and resources much more easy. This BLE-based system can be integrated with other data transmission protocols and low-power, long-range networks for remote monitoring. Progress of this work into the future entails incorporating low-power GPS receivers for geofencing and development of an application interface for remote monitoring. Any questions are welcome. Thank you very much.